are going to discuss about the engineering mathematics. And as you know that this is not the time to study your class notes, and because there is about 30 to 40 days in your gate examination. That's why now this is the time to read your short notes and practice the questions as much as you can. So today we are going to discuss about the short notes of engineering mathematics. If we talk about the engineering mathematics has a very good weightage in your gate examination. It has 14 to 15 marks weightage in all the branches like mechanical, civil, CS, electrical. So this is the subject that has very good weightage in your gate examination. So today we are going to discuss about the short notes. As you know that in your short notes we discuss about the key points and formulas, and after reading that we practice previous year questions of gate examination, your tertiaries and other sources from where you can practice your numericals. So our first topic is linear algebra. In linear algebra we will study matrix and determinants. As we know, the determinant is only defined for square matrix. Here we can see the determinant is only defined for, as we know, determinant is only defined for square matrix. If there is a square matrix, then only there will be a determinant. As we can see, here is 3 by 3 matrix. So then what will the determinant? This is the short formula. Actually this concept is called as Cramer rules, in which this concept can be applied only in 3 by 3 matrix. Three by three matrix, in which how we solve this, in which these is elements, multiply these plus multiply these elements, and this sum is called lower side. This is called upper side because we are going from lower to upper. So this is the upper side, and here 1 multiplied by 2 multiplied by 1, this is going to be 2. So this is 2 plus 2 multiply 3, 3 multiply 1, it's going to be 6, and then 1 multiply 1 multiply 5, this is 5, and the sum is going to be 13. And the upper side, this is first, second and third multiplication, and then we add them, and the determinant A will equal to lower side minus upper side. This is the short trick to solve the 3 by 3 determinant of 3 by 3 matrix. The next point is when diagonal elements are same and all other elements are same in a determinant. As we know, the determinant is only defined for a square matrix. In this, if when diagonal elements are same and all other elements are same, then this is the short tricks. Here we can see that diagonal elements are x, and all other elements are a. All other elements are same and diagonal elements are same. Then the solution will be x plus 3a, x minus a, x minus a, x minus a. Its order is 4 times. There are 4 terms in brackets: 1, 2, 3 and 4. Now we comes to the properties of determinants. You always keep in mind that determinant is only defined for a square matrix. If there is a matrix of order 2 by 2, 3 by 3, 4 by 4, then only you can write the determinant and you can solve that. The first property is the transpose A. Determinant of transpose A is going to be equals to determinant of A. And now second is multiplication of AB. Determinant of multiplication of AB is equals to determinant of A, determinant of V. But summation of two matrices, determinant of summation of two matrices is not going to be equal to of determinant of A plus determinant of B. And the next is determinant of A inverse is equal to 1 upon determinant of A. This is a very important concept. This one and this one. 1, 2 and 3. These three concept is very good. The question has been come in previous years. The next is the determinant value of a triangular diagonal matrix is a product of leading diagonal element. This is the leading diagonal. This is called the leading diagonal. So here it is said that determinant value of a triangular diagonal. If there is a triangular matrix is, as you know, that triangular matrix is the 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 product of leading diagonal element. Leading diagonal elements, the below elements of leading diagonal elements are zero, or the elements of the leading diagonal elements are zero, then it is called the triangular matrix. And if the diagonal elements except diagonal elements, all elements are zero, then it is called the diagonal matrix. In diagonal or triangular matrix, the determinant value will be the product of its diagonal elements. Product of diagonal elements. If each element of a row or column is 0, then determinant is going to be 0. The next is if two row or column are identical, then determinant is going to be 0. If two row or columns are proportional, then determinant is going to be 0. Square matrix is said. A square matrix is said what? A square matrix is said symmetric if transpose of A is equal to A itself. Then square matrix is called as symmetric matrix. It is these three matrices are very important. First, second, and third. The second is skew symmetric. Skew symmetric matrix. If the transpose of A is equal to minus times of A, then it is called skew symmetric matrix. Orthogonal matrix. Orthogonal matrix transpose A multiplied by A multiplied by A transpose of A is equal to unity matrix. Then it is called as orthogonal matrix. After some time we will study about the other properties of symmetric, symmetric and orthogonal matrix, and the questions comes from that concept, such as the determinant value of skew symmetric matrix is always be will always have the absolute value of 1. Next we comes to the next point, that is every square matrix can be expressed as sum of symmetric and skew symmetric matrix. If suppose there is a matrix, that is there is a matrix, and that is just for a second. As we know, this is the every square matrix can be expressed as sum of symmetric and skew symmetric matrix. Suppose there is a matrix, and that is matrix A. Then with the help of symmetric matrix, if we symmetric matrix A plus transpose of A, then it will be the symmetric matrix. A plus AT, it is a symmetric matrix, and A plus AT by 2, it will always be symmetric matrix, and this will be skew symmetric matrix. So a symmetric matrix can be written in the form of the sum of these two matrices. A plus AT also symmetric matrix, A minus AT also skew symmetric, transpose of A, transpose of A. Determinant value of a non-zero skew symmetric matrix of even order is perfect square. This is a very important point. Determinant value of a non-zero skew symmetric matrix of even order. What order? Even order is a perfect square. Then determinant value of a orthogonal matrix. Determinant value of a orthogonal matrix is always be either 1 or minus 1. It means the absolute value will be 1. And multiply A multiply by K, determinant, if we can take K out of determinant A, then it will be n times. If A is a matrix of n order, n by n into n order. If A is non-singular matrix of order n, then determinant is 0. If A is non-singular matrix of order n, then if it is given that A is a non-singular matrix means the determinant is non-zero. Matrix of order n, then A inverse is going to be adjoint of A divided by determinant of A. And second thing, adjoint of A, determinant of adjoint A is going to be equals to of n minus 1 power of determinant of A, where A is a matrix of determinant of matrix of order n into n. Then adjoint of A, determinant of adjoint A is going to be equal to a to the power n minus 1, and adjoint of A, determinant of adjoint of A is going to be determinant of A की power n minus 1 की power 2. As I already told you about these properties earlier. For 2 by 2 matrix, it is a very good concept and question has been come earlier. These two terms are replaced, interchanged, A and D. D will be replaced, will come here, and A will move to here. And these two terms, signs of these two terms will be changed and they will remain at their same place. And these terms AD minus BC will come below. Now, determinant value of a skew symmetric matrix of odd order is always 0. This is a very important point. Determinant value of a skew matrix of odd order. What order? Odd order. Is always 0. Determinant value of skew symmetric matrix of odd order is always 0. Now we come to the next point. For 3 into 3 matrix. As we know, if we have to write the adjoint of A, first we will write here 1. We will start from middle row and middle element. Here we will start from here and then goes to that point. First we will write 1, then we will write 2 minus k 2, then we will write minus 2, and then we again write here 1. In the same way, then we will come to this column, then we will come to this column, and again we will write this column here, first, second, third and fourth. If A m into n, v into n by p multiply the number of multiplication and addition. Multiplication is going to be m and p, and addition is going to be m p n minus 1. This is a very good formulas, but in mechanical there is rarely a question comes from this concept. Rank of the matrix. Order of highest order non-zero minor is called rank of the matrix. Rank of null matrix is taken 0 always. Rank of a singular matrix means determinant is 0. Rank of a non-singular matrix is its order. Rank of non-singular matrix is its order. Rank of a singular matrix means determinant is 0. Rank of singular matrix is less than its order. If A is m into n matrix, then rank of A is going to be less than or equal to minimum of m and n. If A and V are matrices of same order, then rank of A plus V is going to be less than or equal to sum of rank of A plus rank of V. It means cannot exceed the sum of two rank of matrices. Now we come to the next point. Rank of A is equal to rank of transpose of A. Rank of AV is less than or equal to minimum of rank of A and rank of V. In a matrix, if all rows or columns are identical or proportional, then its rank is 1. These points are very good. You have to remember all these points. When will you attempt your question paper? You should keep these points in your mind, because 1 marks question can come from this concept. If rank n minus 1, then rank of A is n into n matrix with rank n, then rank of adjoint of A is going to be n. If rank of matrix is n minus 1, the rank of adjoint A will be 1. If rank of matrix of n order n by n order is n minus 2, then rank of adjoint A will be 0. These are very good points, so remember them. No effect of row or column interchange on matrix. Yes, there is no effect of row or column interchange on a sign of a matrix. Echelon form. Number of zero before non-zero element, number of zero before non-zero element in a row are less than such number of zeros in the next row. So number of zeros will be increasing as we go down to the row, one row, second row, third row, the number of zeros will be increasing. Zero row, if any, must follow non-zero. If there is a zero row, all elements is zero, then it will follow a non-zero row. Means we will keep this row at the last. The number of non-zero rows is called rank of a matrix when it is a row echelon form. After writing the matrix in the row echelon form, then the number of non-zero row is called the rank of a matrix. Normalized vector. Normalized vector of x1 is given by x1 is divided by I will say, suppose there is a vector 1, 2 and 1. Then we will square this and square this and square this, and then we will add the three values and divide x by them. It will be the value of normalized vector. Now we come to the system of linear equation. System of linear equation will be two types. There will be two types of equation. One will be homogeneous and the second will be non-homogeneous. Homogeneous equations are always consistent and they are called trivial and have zero solution if rank of a is number of variable, means determinant of a is not equals to 0. If it will be said that it will have non-zero solution if rank of a is going to be less than number of variable and determinant is going to be 0. Now comes to the non-homogeneous. Non-homogeneous will be said inconsistent if rank of a is not equal to rank of ab, and consistent if rank of a is equals to rank of ab. If the equation is inconsistent, then there will be no solution of equations. If equation is consistent and rank of a is equal to rank of ab is less than number of variable, then it will have infinite many solution. And if rank of a is equal to rank of e is equals to number of variables, then it will have unique solution. Now come to the next point. Free variable, number of independent variable. Free variable is also called as number of free variable. Dimension of matrix of space, dimension of space of solution, nullity, total number of variable, and it is equal to total number of variable minus k rank. So how will we find our free variable? We will find our free variable by subtracting rank of the matrix from the number of variables. Now we come to the orthogonal matrix. Orthogonal vectors. If transpose of one vector multiplication of second vector is equal to 0, then it will be called as orthogonal vector. Now come to these are not the important points, so we will skip them, and we will come to the eigenvalues and eigenvectors. The roots of characteristic equation a minus k lambda is equal to 0 are known as eigenvalues, and each eigenvalue will have its eigenvectors. So after solving this, we will find the eigenvalues, and after this we will find the eigenvectors. It is eigenvector. X is eigenvector corresponding to this eigenvalue. Eigenvector corresponding to, now this is the line, eigenvector corresponding to the distant eigenvalues. This is important point. Distant eigenvalues of a real symmetric matrix are always orthogonal. If all leading minors of a real symmetric matrix are positive, then all its eigenvalues is positive. Now we comes to the next point. The eigenvector corresponding to the distant eigenvalues are of any square matrix, always linear independent. The eigenvector corresponding to the repeated eigenvalues of any square matrix will linearly independent or dependent or independent. So if there is the eigenvector corresponding to the repeated eigenvalues, if there is a repeated eigenvalues, means suppose there is a eigenvalue that the value of eigenvalue is 2, so the eigenvectors may be linearly dependent or linearly independent, maybe. But for the distinct eigenvalues, the corresponding eigenvectors will always be linearly independent. Algebraic multiplicity, number of times an eigenvalue repeated, means a eigenvalue repeated of 2 times, then algebraic multiplicity is going to be 2. If an eigenvalue comes 3 times, then algebraic multiplicity is 3 times. No linearly dependent eigenvector corresponding to a repeated eigenvalue. This is a very good point. And what is this? Sum of eigenvalues equal to trace of the matrix. Suppose eigenvalues are lambda 1, lambda 2, lambda 3, then trace equal to trace of matrix. The product of eigenvalues is going to be a determinant of matrix. This is a very, very important point. The eigenvalues of transpose of A, eigenvalues of A. All these points are very important. All these points are very important points. Eigenvalues of triangular matrix or diagonal matrix, leading diagonal elements. If lambda is an eigenvalue is of a non-singular matrix, 1 upon lambda is eigenvalue of A inverse. This is a very good point. Is a eigenvalue of adjoint A. If lambda is an eigenvalue of matrix A, then eigenvalues of A square. These points are very important. Keep in mind, all these points are very important. So the eigenvalue of A square is equal to lambda square e power n equal to lambda to the power n. These points are very important. And this point is not important, but always remember the eigenvector of A inverse adjoint A square, A cube, A to the power 4 are always same. Very easy to remember. In a square matrix, if n rows are identical, then compulsorily n minus 1 eigenvalues will be 0. And this is the next point. If there is a matrix, there is a 4 by 4 matrix, means order more than 3 by 3, 4 by 4 matrix, 6 by 6 matrix, or 8 by 8 matrix, in which these terms is 0, or this single terms, these terms is 0, means the terms here is 0, or the terms here is 0, then we can write them this way. Then we can write them in 4 rows and we can solve them. And if we can find out, the question really comes from this concept, and you can find out the value of eigenvalue. Now our next point, transjugate of a matrix. What is the transjugate of a matrix? Transpose of conjugate of a matrix. Transpose of a conjugate of a matrix is known as transjugate of a matrix, denoted by a to the power theta or a to the power t. A to the power theta or a transpose of a to the power a bar. A square matrix is said to be Hermitian matrix if these 3 points is going to be very, very important. Point 1, point 2 and point 3. A square matrix is said to be Hermitian matrix if a to the power theta is equal to a. A square Hermitian matrix if a to the power theta is equal to minus a. Unitary matrix is equal to a to the power theta is equal to a. Conjugate matrix multiplied by a is equal to I. Now these are the very, very important parts. This is the eigenvalues of a Hermitian matrix. The eigenvalues of a Hermitian matrix says or a symmetric matrix. Eigenvalues of a Hermitian matrix or symmetric matrix are always reals. 5 to 10 times question has been come from this only this point. 5 to 10 times. Keep in mind. The eigenvalue of a skew symmetric matrix or a Hermitian matrix are either 0 or purely imaginary. This is also a very important point. And the next point is also a very important point. The eigenvalue of a unitary matrix. Unitary matrix or orthogonal matrix. Unitary matrix and orthogonal matrix have absolute value of 1. Absolute value of 1 means determinant is always 1. Now the second next point is not so important, but question can come. Every square matrix, that is question can come. Every square matrix, its characteristic equation, it is used to find a and m, a n minus 1. Every square matrix satisfy its characteristic equation. So this was the short notes. These were the short notes of our topics linear algebra. And now please study only short notes, because now there is not enough time to read all your notes. I'm repeating that again. Read your short notes and then practice your questions. So next we'll come with next topic, our next topic. So till then, bye bye.